What's up? Can a low come up in your crib?
Man, fuck you. I'll see you at work.
Oh, nigga, don't hate me because I'm beautiful, nigga. Maybe if you got rid of that old yee-yee ass haircut you got, you get some bitches on your dick. Oh, better yet, maybe Tanisha will call your dog ass if she ever stop fucking with that brain surgeon, the lawyer she fucking with. Nigga.
What? Oh,
Every time you turn on a game, a world exists, with its own light, and its own weather, and its own laws of physics, and that is being rebuilt completely from nothing 60 times every second for as long as you keep playing. All this is possible because of game engines. A game engine is a software development environment. Every game has a game engine, whether on console, mobile, or PC. Game engines are expensive and take time to create from scratch. This is why game engines are often economized, meaning the same game engine is used for multiple games, as well as when we port games to multiple platforms. Its core functionality include a rendering engine, a physics engine, an audio engine, scripting, animation, artificial intelligence, networking, streaming, and localization. And it may optionally also include cinematics. If you're developing, you need to decide what is more important and what engine can be used to maximize it. In this video, we will cover the machine underneath games, the actual mathematics, physics, and engineering that has to happen layer by layer before a world exists. If you are the kind of person who has ever paused a game just to admire the graphics all the way down, rendering, physics, environments, characters and NPCs, and how their audio and voices are integrated, this is the video for you. The history and evolution of video games. Historically speaking, in the early 1980s, there is no such thing as a game engine because there was no room for one. Games were written directly against the hardware in assembly language, all from scratch. The development of further generations of coding languages made things simpler over the years, with now modern engines having the foundation of C#, JavaScript, Python, and C++, and many others. Every engine since is built from the same handful of core subsystems that we will explore today. Let's start with the subsystem that does the most visible work of all of them, the rendering pipeline. All games and all their elements are essentially made out of triangles. It's how these triangles are coded or directed that makes all other things possible. A face in a modern game might be built from 20 or 30,000 of these triangles, small enough and numerous enough that your eye stitches them into something that looks smooth. A whole open world environment might use hundreds of millions, spread across everything the camera could possibly see. This collection of triangles connects edge to edge into the single connected shape called a mesh. And the mesh is the actual literal skeleton of everything you see. Every character, every rock, every teacup starts as a mesh, a cloud of points in space called vertices, wired together into triangular faces. Why triangles, you may ask? Because a triangle is the only polygon that is mathematically guaranteed to be flat, no matter where you put its three corners. Any 3 points in space define exactly one flat plane. They are the simplest unit of flat, and flat is what the graphics processor is built from the silicon up to calculate extremely fast, in parallel, millions of times per second. So, step 1 of rendering anything is by building a mesh. That mesh on its own is just geometry. A wireframe of shapes, no color, no texture, nothing. It's the skeleton before the skin. The skin comes next, and it comes in the form of a texture, which, despite the name, is really just a flat ordinary image that gets wrapped around the three-dimensional mesh. The process of telling the computer exactly how that flat image should fold and stretch around the three-dimensional shape is called UV mapping. But a flat color texture alone still looks wrong because it doesn't respond to light. So, modern engines wrap several, stuck together, each one answering a different physical question about the surface. There's the base color texture, which is just raw pigment. There's the roughness texture, which tells the engine pixel by pixel how rough or how mirror smooth this surface is at a microscopic level. There is a metallic texture marking which parts of the surface behave like metal, where it reflects almost all light and absorbs almost none, versus parts that behave like an ordinary non-metal, called a dielectric, which absorbs some light and reflects the rest diffusely. And there is a normal map, which fixes bumps and wrinkles without adding a single extra triangle to the mesh by encoding in the colors of an image the precise direction each tiny patch of the surface should appear to be tilted, so that light calculations bend around fake detail that isn't really there in the geometry at all. This entire approach is called physically based rendering, or PBR, and it's arguably the single biggest visual leap games made in the 2010s. Before PBR became standard, artists were essentially hand painting how shiny or matte something looked for one specific lighting setup, and objects would frequently look subtly wrong the moment you moved them into a different scene. PBR ties material properties to real, measurable physical behavior. The engine is actually running a simplified version of real optics to figure out how light should bounce off it, rather than an artist guessing. Then there is rasterization. Picture your triangle floating somewhere out in the game's three-dimensional world. The engine has a virtual camera, which is usually your point of view, and it needs to figure out where the triangle would land if you flattened the whole scene onto a 2D grid the size of your screen. So it does exactly that. It mathematically projects every corner of every single visible triangle onto that flat grid. Once the triangle's three corners have a position on that flat grid, the engine fills in every pixel that falls inside the triangle's edge, and for every pixel that is inside, it runs a small specialized program called a fragment shader or a pixel shader, whose whole job is to answer one question. Given this triangle's material, this point's normal direction, and every light source in the scene, what color should this single pixel be? This happens for every pixel that the triangle covers, which for a moderately complex scene can mean billions of these tiny colors calculations every single occasion. This is the actual reason graphics cards exist as separate specialized hardware from the main processor in your computer. A normal processor is built to do a few things at a time, extremely fast and extremely flexibly. A graphics processor is built to do one simple thing: shade a pixel millions of times simultaneously in parallel, because pixel shading is what mathematicians call embarrassingly parallel. The answer for one pixel almost never depends on the answer for the pixel next to it. So you can hand every pixel on its own tiny calculating unit and let the thousands of them work at once. Rasterization is astonishingly fast, which is exactly why it has become the standard approach for real-time graphics. It's very good at figuring out where a triangle is, and not naturally good at figuring out how light actually bounces around a scene realistically. A rasterizer, by default, only knows about direct light traveling in a straight line from a source to a surface to the camera. It doesn't inherently know that light bouncing off a red wall should tint the nearby floor slightly red, or that a mirror should show a reflection of something behind the camera. Which brings us to a second, newer approach, one you have almost certainly heard of, even if you didn't know exactly what it meant: ray tracing. Ray tracing ensures that when that ray hits something, the engine doesn't stop. It can bounce the ray again off the surface it just hit to see what light that surface itself is receiving. It traces an approximation of the light's actual path. It's only in roughly the last several years that specialized hardware built specifically to accelerate what does the ray hit calculation has made real-time ray tracing possible at all inside video games. Even now, most video games use it selectively, tracing rays only for specific effects like reflections or shadows, while still relying on traditional rasterization for the bulk of the image, because full pure ray traced rendering for every pixel remains too expensive to sustain at 60 frames per second in a very large detailed world. Then we have lighting. Modern games calculate lighting in two broad categories: direct light, from sources the engine can clearly see, like the sun or a lamp, and indirect light, often called global illumination, which is light that is already bounced at least once off some other surface before reaching the point you're looking at. Indirect light is why bounced light finds its way inside dark rooms. Simulating global illumination properly in real time was for a long time one of the hardest unsolved problems in graphics, and engines spend years faking it with pre-baked light lamps. If you shoot out a light bulb in a game using baked lighting, the shadow on the wall behind it often won't update, because that lighting was never being calculated live. It was memorized in advance and painted on like a texture. It's only recently that real-time global illumination, calculated live every frame using ray tracing and clever approximation techniques, has become viable, with light finally being allowed to bounce correctly, live as the world changes around you. Everything we've described, triangles, materials, rasterization, ray tracing, direct and indirect light, happen completely independent of whether anything in that scene is actually moving, or alive, or even real in the game's own internal sense. Because games are not static pictures, they are places with mass, weight, consequences, which means the next thing you're going to talk about is how an engine decides that a wall should stop you and that gravity should feel like gravity. There is a specific kind of vertigo that good open world games are built to produce. The feeling of standing on a hill and being able to see a mountain range 20 kilometers away and knowing you could actually walk there, and that when you arrive, it will be a real, detailed place and not a painted backdrop. There is a very elaborate set of strategies for deciding what deserves detail right now and what doesn't. The first and the oldest of these strategies is called level of detail. The idea is almost embarrassingly simple once you hear it. An artist doesn't just build one version, say, of a distant mountain. They build several at different levels of complexity. A near version, with every rock and crag modeled in full, rainiest detail, meant to be seen from just a few meters away. A medium version, simplified with the fine detail baked into textures instead of real geometry. And a far version, sometimes just a flat painted image, good enough to convince your eye of a mountain shape from a distance where you could never actually perceive the difference anyway. As you move through the world, the engine is constantly, invisibly swapping these versions in and out based on your distance from them, spending its triangled budget only where your eyes could possibly notice. The second strategy is culling, a family of techniques whose entire purpose is to avoid ever calculating anything the camera can't see in the first place. The simplest version is Falstrom culling. Your camera doesn't see in all directions at once. It sees a specific pyramid-shaped volume of space called the view frustum, and anything sitting outside that pyramid gets discarded before the game engine wastes a single calculation on it. A more sophisticated version is occlusion culling, which handles a trickier case, when an object might technically be inside your field of view, but completely hidden behind a wall or a mountain in front of it. Modern engines constantly test which objects are actually blocked from the camera's sightline by other closer geometry and skip rendering anything that's fully hidden, because there is no point pending computation drawing a house that a cliff face is completely covering. Then there's a specific problem of scale that open worlds introduce, which older, smaller games simply never had to face. You cannot load an entire 100 square kilometer map with every texture and every mesh into memory at once. It would be far too much data for any machine to hold simultaneously. So, open world engines use a technique called streaming. The world is broken into a grid of chunks, and only the chunk near to the player, plus a buffer zone slightly further out, are actually loaded into active memory at any given time. As you walk, the engine is constantly, quietly loading the chunks you are approaching in the background and unloading the chunks falling behind you. And the entire craft of making an open world feels seamless without the loading screens and the doorway poses of older games comes down to how well a studio manages to hide that constant loading and unloading from your perspective. This is also, incidentally, exactly why so many open worlds funnel you through a small elevator ride, or a tight winding cave corridor, or a long scripted vehicle cutscene right before a big new area opens up. Those aren't just narrative pacing choices. They're often deliberately engineered stalling tactics, buying the streaming system precious extra seconds to load the next chunk of world in behind the scenes without you noticing. Terrain itself, or the actual ground you walk in, is frequently generated from something called a height map, essentially a grayscale image where the brightness of each point corresponds to how high the terrain should rise at that location. White for a mountain peak, black for a valley floor. The engine reads every image and generates an actual three-dimensional mesh from it, automatically following a set of rules rather than authored by a person triangle by triangle. Some of the most staggeringly large game worlds ever built are procedurally generated at their core, with human designers acting less like sculptors and more like gardeners by planting rules and constraints and letting an algorithm grow the actual terrain, vegetation, and even settlement placements in those rules. From those rules, atmosphere is its own dedicated system in most engines. The fog that thickens with distance partly sells the mood and partly, not coincidentally, to hide the exact distance where far away, low detailed objects fade in and out of existence. Dynamic time of day systems that recalculate the position and color of the sun continuously, feeding new lighting information into everything we discussed in the last chapter. Weather systems layering rain, wind driven vegetation, and volumetric clouds on top of this base world. An environment, though, no matter how convincingly built, is still just a shape. It doesn't yet know that it has walls you can't pass through, or a floor that catches you when you fall, or that the world needs rules. And it means it's time we talk about physics. Gravity in a game engine is not a law of nature, it's a line of code, usually very small, that runs every frame, 60 times a second. But gravity itself will just make everything sink through the floor forever, which is obviously not what happens. That's why we need collision detection, which is the system responsible for figuring out every single frame which objects in the world are touching or about to touch each other. A modern game scene might contain thousands of objects that could potentially collide with each other. And if the engine naively checks every object, the number of checks required explodes catastrophically as the object count grows. So virtually every physics engine handles collisions in two distant passes. The first pass, called broad phase, isn't trying to calculate at all. It's trying to be fast, using cheap, rough approximation to quickly throw out the overwhelming majority of objects pairs that obviously could possibly be touching because they are nowhere near each other. Only a small handful of pairs that survive that rough get promoted to the second pass, called the narrow phase, where the engine finally does the expensive, precise math, checking the exact detail, checking the actual detailed shape of each object, not just its rough box, to determine exactly where and how hard they are really touching. And this raises an important, often surprising point. The shape of the engine usually for collision, is often not the same shape you actually see rendered on screen. A wildly detailed character model with individually sculpted fingers and flowing hair would be absurdly, needlessly expensive to run collision math against directly. Every character is wrapped in a simpler visible shape underneath, or a capsule, most commonly wrapping the whole body, limb per limb, standing in for the whole body, or a small skeleton of simplified boxes and spheres for more detailed ragdoll physics. Once the engine knows two things are touching, it has to decide what happens next, and it tracks it continuously: its mass, its current velocity, and its current rotational spin, and the forces currently acting on it, like gravity or impact against another object. This is what turns into ragdoll physics. The moment a character dies after being knocked out of a vehicle, or stumbles down a staircase, or falls down from a building with gruesome realism, what actually happens under the hood is a handoff. Until that moment, the character's body was being controlled by the animation system with handcrafted, mostly pre authored movements that we'll discuss later in this video. But the instant the ragdoll triggers, control gets handed over to the physics engine, which now treats the character's skeleton as nothing more than a loose chain of separate bodies connected by joints with realistic limits on how far they can bend, and simply lets gravity, momentum, and collision take over completely. This is precisely why ragdoll deaths sometimes look horrifyingly perfect and sometimes look absurd and comedic. Physics always runs consistently, regardless of machine power. It must be perfectly consistent and repeatable because physics determines the actual gameplay outcomes. Fixing physics to a steady, predictable rate keeps the actual rules of the world identical for every player, and it's the rendering system's job to do it. That combined produces something players almost never concisely notice, and it's exactly the point: the weight. Now, let's talk about animation. Every time the engine asks the graphics processor to draw something, it has to send over what's called a draw cell, a small packet of instruction telling the graphics hardware what to render next. Every draw cell carries a fixed cost paid by the main processor to prepare and hand off the instruction. And if a scene requires a separate draw cell for every single object, let's say a forest with 50,000 individual trees, could mean 50,000 separate handoffs every single frame, and the overhead of just organizing all those handoffs, quite apart from actual drawing, could bring even a powerful machine to its knees. The solution engines lean on is called instancing. If you have a large city of 5,000 buildings, and a large number of them are actually of the same building model, just repeated at different positions, rotations, and sizes across the city, there's no need to describe that building's geometry 5,000 separate times. Instead, the engine describes the building's shape exactly once and then hands the graphics processor a single, much larger list of instructions, all bundled into one draw cell instead of the 5,000. This is precisely how games manage to fill a screen with dense, scrolling crowds or thick forests without collapsing under its own geometry. Another trick is called batching. Even when objects are identical, if they share the same underlying materials and texture, engine can often merge many small objects into one larger combined mesh behind the screens, purely to reduce the number of separate draw calls needed, even though visually nothing about the scene has changed at all. This is where the level of detail, which we introduced earlier, turns out to be doing double duty. It's about reducing draw call overhead, because a simplified distant version of an object can sometimes be batched and instanced far more aggressively than a full detailed version ever could. The visual result is a dense, living, detailed world that only the time you notice it is when it fails and the game stutters and have weird bugs. It's time we talk about how a character gets placed into games. So, before a character can move at all, an internal skeleton. That skeleton inside an engine is called a rig, and it's built from a hierarchy of invisible points called bones or joints. A root bone at the hip with a collarbone attached to it, a shoulder bone attached to the upper arm and then the lower arm, and the bones cascading outwards, each one defined not by its own absolute position in space, but by its position and rotation relative to its parent. This parent-child structure is the whole trick. If you rotate the shoulder bone, every bone attached beneath it, the upper arm, the lower arm, the hand, and the individual fingers automatically inherit that same rotation and swings along with it. Exactly the way your actual forearm swings along automatically when you rotate at the shoulder without you having to separately think about moving your forearm at all. Once that invisible skeleton exists, it has to be connected to the visible mesh sitting on top of this. This process is called skinning. And this is where the most enormous amount of unglamorous, painstaking artistry lives. For every single vertex making up the character's mesh, an artist, or increasingly a semi-automated tool, has to decide which bone or bones influence that particular point, and by how much. A vertex sitting right in the middle of the upper arm might be almost entirely controlled by the upper arm bone alone, but the vertex near the elbow, right at the bending point, usually needs to be influenced by both the upper arm and the lower bone simultaneously, blended together in some carefully tuned proportion, because it has to be controlled by only one bone, or would visibly tear and pinch at the joint, revealing the character to be nothing more than a rigid, disconnected shape stamped together. Getting the influence weights right, especially around difficult areas like shoulders, hips, and the base of fingers, is some of the most tedious and detailed obsessed labor in the entire animation pipeline. And it's almost invisible when done correctly. It only comes visible to the player when it gets buggy. So now we have a mesh wired to a skeleton that bends convincingly. But bending isn't the same thing as moving with intention. For that, the skeleton needs to actually be told how to pose itself, frame by frame, and that there are two fundamentally different philosophies engines use to make this happen. The first one, and overwhelmingly the dominant one, is called keyframe animation, built on motion capture and hand animation. A real performer wearing a suit covered in tracking markers physically acts out a walk, a jump, a sword swing in a motion capture studio, and the specialized software translates the captured movements of these markers into the series of skeleton poses over time. That recorded sequence, called an animation clip, gets loaded into the engine as pre-authored data. The second philosophy, used far more selectively because it's considered more computationally demanding to get right, is procedural or physics-influenced animation. Here, the motion isn't fully pre-recorded at all, but calculated live in response to the actual environment the character finds itself in. The clearest, most intuitive example is a technique called inverse kinetics. In inverse kinetics, the logic is that you specify where you want the hand to end up, and the system works backwards. Mathematically, solving for what the elbow and the shoulder rotations would have to be to actually place the hand there correctly. Adjusting a pre-recorded animation clip on the fly to fit terrain or props the original motion capture performer never actually saw or interacted with. This is exactly the technology behind a character's feet correctly planting on an even, sloped ground instead of floating above it or clipping through it. Now that we have a moving body, the next question is, how do NPCs' decisions actually come from? Every NPC is running a structured decision system built entirely out of roles, conditions, and pre-authored behavior. The oldest and simplest tool for building this illusion is the finite state machine, and it's worth understanding because you can see its bones showing in every game you have ever played once you know to look for it. A finite state machine works exactly the way it sounds. An NPC exists at any given moment in exactly one clearly defined state, and the character's behavior is entirely dictated by which state it currently occupies. A character can walk in a fixed route and periodically checks whether it can see the player. The moment that check succeeds, the character transitions into an alert state, which may trigger a different set of behaviors. Let's say it can play a surprise animation, or start moving towards the player's last known position, or begin the attacking state's condition. Every one of these states is a self-contained little box of pre-written behavior, and the entire personality of the character is really just a set of specific rules and states it has, and the specific way it can jump between them. Finite state machines are simple, predictable, and extremely easy to debug, which is exactly why they were the industry standards for decades, and why they are still constantly used today for simpler characters. But they have an obvious weakness. They have a finite number of ways for an NPC to act before they can get very buggy. This is the exact problem that a more flexible tool called a behavior tree was built to solve, and it's become, over roughly the last 2 decades, the closest thing the industry has to a standard for anything more sophisticated than a very simple enemy. The behavior tree organizes an NPC's decision making not as a flat set of states, but rather as a branching hierarchy of smaller tasks and questions, evaluated from top down, every single frame in a specific order. In the very top might be a broad question like, is the player currently visible? If the answer is yes, the tree branches down a whole subset of combat related behavior, like, is the player in melee range? Or is my weapon ready? Or do I have allies nearby to coordinate with? Each one of these, in turn, branches further into more specific concrete actions. The genuine power of this structure is reusability and clarity. Designers can build small, well-tested branches once as modular building blocks and then mix, match, and reorder those blocks across dozens of different enemy types, giving an entire cast of different creatures wildly different apparent personalities just by rearranging the existing branches in a priority order without a new single line of code being written. A close and increasingly similar method is called utility-based AI, which handles a specific weakness that trees can struggle with. Situations where several possible actions all seem reasonable at once, and picking the genuinely best one depends on weighing several competing factors together, not just allowing a fixed priority order. Instead of a rigid branching tree, utility systems score every possible actions a character could take right now. This is why some of the most sophisticated NPCs you'll encounter feel less like they are following a fixed script and more like they are weighing down options, even though underneath it's still entirely a set of rules and arithmetics, just considerably more nuanced arithmetic than a simple state machine allows for. None of this decision making means anything though if the character can't physically get there, and this brings us to a path finding system, or the machinery responsible for figuring out an actual walkable route from an NPC's current position to wherever its behavior tree has decided it has to be. A simplified, walkable surface only version of the level geometry, calculated in advance, that strips away everything except the flat, traversable ground the character could actually stand on, ignoring walls, ceilings, and any decorative geometry that isn't actually walkable at all. Once that simplified walkable surface exists, finding a route across it becomes a well-studied solvable mathematical problem, commonly handled by an algorithm called A-star, which explores a nav mesh outwards from the character's current position, intelligently favoring paths that seem to be heading towards the destination in the shortest, genuinely walkable route. The same fundamental algorithm, incidentally, that powers many directional maps we have today. NPC perception. A well-built enemy doesn't simply, instantly know where you are the moment you're anywhere nearby. It has to be given a simulated set of senses, usually a vision cone representing a limited field of view out of some maximum distance, often combined with a hearing radius that reacts to noise, so that a footstep, a gunshot, or a shattered window can alert a guard even without a direct line of sight. Genuinely well-tuned enemy perception is often gradual rather than immediate, precisely because designers have learned through decades of player frustration that enemies who react instantly and perfectly the moment you are technically visible feels less than a believable world and more than an obvious and fair, all-seeing machine, and hence giving NPCs human-like simulation of doubt. All these take together gives a good NPC. For characters and NPCs to actually talk to you, they need a whole separate system for that. And that's where dialogue systems come into play.
What's up? Can a low come up in your crib?
Man, fuck you. I'll see you at work.
Oh, nigga, don't hate me because I'm beautiful, nigga. Maybe if you got rid of that old yee ass haircut you got, you get some bitches on your dick. Oh, better yet, maybe Tanisha will call your dog ass if she ever stop fucking with that brain surgeon, the lawyer she fucking with, nigga.
What?
The foundation almost every branching conversation is built on is called a dialogue tree. It's a tree structure that branches between lines of speech. Each node in the tree is a single line or block of dialogue, and each one has several children, the possible player responses, or the possible ways the conversation could continue, with the actual conversation experience being one specific path traced through that much larger tree. A game state tracks what you've already said to this character, what quests you have completed, and what the character currently thinks of you. Whether you are carrying a specific item they'd react to, or a well-built conversation might quietly check a dozen of such variables. That authored structure then gets exported into the actual game engine as data, which the dialogue system reads and executes in runtime. Two more pieces complete this illusion. First, localization. Every one of these tree nodes needs to exist not only in the game's original engine, but frequently in dozens of other engines, which means the dialogue system isn't really storing English or Japanese or Spanish text directly at all. It's storing an abstract identifier for each line, a kind of internal reference number, and looking up the actual displayed text in whatever language you've selected from a separate translation table at the moment the line is spoken. The entire branching structure of the conversation can stay completely identical across every language version of the game. And second, when the dialogue is voiced rather than its written, a specific challenge of lip syncing is needed. The most common automated approach analyzes the actual recorded audio wave, breaking spoken sound down into a sequence of phonemes and mapping each detected phoneme to a corresponding facial pose called a VSIM, blending rapidly between them as the audio plays, essentially reverse engineering a plausible mouth shape from the sound alone, entirely automatically. Now let's move to cutscenes. There are two fundamentally different ways a game can show you something it doesn't want you to control. First, the older approach is the pre-rendered cutscene, a sequence that is not actually running on your machine in real time at all. It's a finished original video file, rendered once in advance, often in powerful offline computing hardware far beyond what any player's console or PC could sustain in real time, frame by frame, with none of the strict 60 times per second pressure that ordinary gameplay rendering has to live under. That's precisely why older pre-rendered cutscenes would look almost embarrassingly better than the actual gameplay surrounding. They weren't obeying the same rules at all. They were just animated film, exported as video, and simply played back as one, while the game briefly handing control to a video player, before returning it to the real engine when the video ends. The second, and today by far the most common approach for major story moments, is the in-game cutscene. And this is where things get genuinely more interesting from an engineering standpoint. Because an in-engine cutscene is the exact same real-time rendering engine we've spent this whole video describing. The same triangles, the same shaders, the same skeletal animation, and simply being driven by a highly detailed, pre-planned script instead of your controller input. The obvious advantage is consistency. It's genuinely the same engine and the same character models as regular gameplay. An in-game engine can reflect your actual customized character, your actual equipped gear, decisions you've made hours earlier, and none of which a pre-rendered video baked in advance before any of that context existed could ever account for. Making that work smoothly requires a specific category of tool most engines now build in directly, called a sequencer or timeline system that ensures even physics and rules are followed, even in that cutscene. Camera work during a cutscene behaves completely different from the camera work during gameplay. During a cutscene, the camera is instead being explicitly and deliberately directed. Using the same principles a film cinematographer would use operating entirely inside the game's real-time rendering, with none of the constraints ordinary playable gameplay cameras have to respect. Some use full performance capture for more elaborate performances inside these cutscenes, so that the character's grief or restrained anger during a cutscene is very clearly portrayed rather than an animator's interpretation of what that grief would look like. Some older games instead used full motion video, real filmed footage embedded directly into the game in place for any in-game pre-rendered 3D cutscenes. All of this we have talked about, physics, animation, AI, dialogue, and cinematics, still depend on one final link in the chain, and that's the control mechanism and how a character actually moves on screen on command. It starts with input pulling, which is the process of the engine asking the controller or keyboard over and over whenever a button is pressed or whenever the joystick gets tilted, then reads it as raw data, after which it acts upon it, precisely allowing the character to creep forward slowly with a gentle stick tilt and sprint into a full one using the exact same input, read with different intensity. That raw input then has to travel through a character's controller, the specific system separate from the general physics engine we described earlier, responsible for the translating action to the character actually reacting in that way. All this large amount of deliberately hand-tuned game-specific logic on top of raw physics, definitely defining exactly what counts as walkable ground, how a jump's arc should feel, or how a character's acceleration from standing still to a full run pans out to be, is covered by the next one. Next is input buffering. This is where the action is delayed until it's logically valid. For example, if you press the button to jump while in the air, after a jump action is in order, then the jump is done once the character is on the ground again immediately. It's what ensures combos exist in video games. If a player presses several buttons in rapid succession, the reverse version of this same generosity is often called coyote time. Many platformers deliberately allow you to still successfully jump for a short grace window after you've already walked off the ledge, quietly forgiving input that arrived late, purely because it makes the controls feel more responsive and fair. And finally, all this has to survive the brutal reality of latency, the unavoidable physical delay between your thumb pressing and that signal actually completing its full journey through the input pulling system and into the character, which finally translates through the processor and the controller what the action of the character pans out to be. Now let's cover game loop. At its absolute core, a game loop is nothing more than following the events that have occurred or have been triggered and then rendering the current state of that world on the screen, then doing it again and again 60 times a second or as close to that as the hardware allows, as long as you keep playing. The game loop is the single shared heartbeat that all the functions synchronize against, each one against its own small piece of work once per cycle before handing control back to the loop to move on to the next system, and eventually the rendering step, which gathers up the freshly updated state of absolutely everything and finally turns it into the single state you actually see. All this is done in delta time. This is exactly why a well-built game plays at the same actual speed whether it's running on a very fast machine producing a great many loops per second or a slower machine producing fewer, because every single one of these systems constantly correcting itself against real lapsed time rather than naively consuming a fixed uniform rhythm that hardware in reality can never perfectly guarantee. And that's it, guys. Now you know how games are made. Thank you for watching and subscribe.